Okay, we've seen that if we select 3 data points, we can write the equations for the quadratic model, y equals at squared plus bt plus c, and we expect to get an exact solution. We expect to get a solution to those 3 equations, and if we get an exact solution, then the function we get for those values of a, b, and c should exactly match the data for these 3 selected points. We can't expect it to match for these 2, though. The one that matches these 3 probably won't match these 2. If we choose 3 other points, there'll still be 2 points that the solution won't match. So, what do? Well, let's go ahead and write down all 5 equations, so we can check and see that these are the correct equations. Okay? What we want to do is we want to find the values of a, b, and c that come as close as possible to predicting the values of y. If we plug in the t into our resulting equation, having gotten the best possible values of a, b, and c, we should be able to get predicted y values that match these as closely as possible. So, we want to find the model that works best, in other words, for all 5 points. Okay, well, our matrix equation, well, right there it is. This system of equations clearly is the same as this matrix equation, and this equation is the form ax equals b, where x is your a, b, c that you're trying to find. Now, there's no exact solution, so what we want to do is find the x that makes ax as close as possible to b. Now remember, x is going to be an a, b, c, so if we find the x that makes this as close as possible to this, then we'll have an a, b, and c, which when plugged in here, in some sense, gives us the model that best predicts the correct values of y when we plug in the values of t. Now observe, we do not expect to get an exact solution here. Okay, I've said we don't. Why don't we? Well, we have too many equations for unknowns. For the unknowns, we've got 5 equations and 3 unknowns. If we take any 3 of these equations and find values of a, b, and c, but those values won't work for the other 2. At least we don't expect that they will. Also, we expect the augmented matrix that we get if we try to solve this system using an augmented matrix to reduce to this form, where these asterisks, there's no reason to expect any of these asterisks to be 0. By coincidence, it might be that 1 or 2 of them do, but we can't expect that. And it would be very rare with real-world data that that would actually happen, that any of these would be 0. So the augmented matrix is going to reduce down to the identity here, but then you're going to have 2 rows of zeros with non-zeros over here, which is contradictory. You're going to have 0 equals something that isn't. Okay, so we don't expect any exact solution. So what are we going to do? Well, the way we do this is we model this matrix equation as a transformation. Okay, we take the A matrix and use it to define the transformation T of V, which is just A V. So that for any vector V, the transformation is equal, the transformed vector is equal to AV. This is a transformation from R3 to R5. And we want to look at the subspaces, the basic subspaces of R3 and R5, and see what we can conclude about our solutions. So we're going to take a quick look at that.